We're going to continue with our unit on gases here, and this actually fits into a couple of the big ideas. We're going to get into big idea 2, which is indicated on the board in great detail in the second 9 weeks, but we're going to start to establish some type of foundation for it. We're going to be talking about gases and specifically gas laws today, and again, all of it is review at this point from honors, so you're not going to find anything that challenging here. What is critically important is that you understand relationships and how to interpret them. So we talked about Boyle's law last time, which shows the inverse proportionality between pressure and volume at constant temperature, and today we want to review Charles' law first, which is the direct relationship between Kelvin temperature, not degrees Celsius, Kelvin, and volume. And Charles said that the volume of a fixed amount of gas at constant pressure is directly proportional to its Kelvin temperature. And you can convert degrees Celsius to Kelvin simply by adding 273. That is provided for you on your formula sheet, which you'll always have on a quiz test and AP exam. They give you this conversion here, so just add 273 to the temperature in degrees Celsius to get Kelvin. Okay, they give you a lot of formulas and constants, and we'll go through that today. They don't give you Charles' law directly, but they do give you the ideal gas law, and you can clearly see the direct relationship between volume and Kelvin temperature, known as Charles' law. So what you're looking at is volume and temperature are directly related. If you're dividing two variables, they're on the same side of the equation and you're dividing them, they are directly related. As one increases, the other increases as well. Some of you last year would have done a lab on this where you started with a gas at a very high temperature because you were boiling it or heating it to a high extent, and then you plunged it into cold water and the volume of the gas decreased markedly. So the relationship between volume and temperature is direct. And you can do very simple types of problem solving here. The first one, it says a sample of hydrogen gas occupies 692 liters at 602 degrees Celsius. If the pressure is held constant, what volume will the gas occupy after cooling to 23 degrees Celsius? The first thing I want to recognize is that I'm cooling the gas, the temperature is decreasing. What should happen to the volume? What? If we're decreasing the temperature, the volume will decrease. They're directly related. In this example here, that's something you want to check at the end to make sure you didn't make any silly mistakes. So in this example here, we've got a volume of 692 liters. You must have an awful lot of gas. The temperature is 602 degrees Celsius. I'm immediately going to cross that out because we don't play in degrees Celsius with gases. We must use Kelvin. Now you're going to cool, so this is the first set of conditions, V1 and T1. You're going to cool the gas. Oh, sorry, 5. That's just bad math. Thank you. 602, right. And then you're going to have 23 degrees Celsius. So that's 296 Kelvin, correct? Okay. And we're looking for the volume. And we said the temperature decreases, so the volume decreases. Now in regard to Kelvin temperature, the factor by which the temperature changes is the same factor by which the volume changes. So you have V1 over T1 equals V2 over T2. We're solving for V2. I know some of you like to put numbers all over the page, but I don't recommend it at this level. It would be much, 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 much better if you manipulated variables. So you're solving here, and you're going to put T2 here, And then you've got 296 Kelvin times 692 liters over 875 Kelvin. And that's going to be 234 liters. So the volume decreased markedly with the decrease in temperature. Charles' law shows the direct proportionality between Kelvin temperature and volume. One thing I definitely want to indicate here, if you look at the temperature in degrees Celsius, you can see clearly that you don't have a direct proportionality between degrees Celsius temperature and volume. Because if you were to divide 875 by 296, you can see that the temperature decreases almost by a factor of 3. But if you divide 602 by 23, that temperature decreases by a factor of 26. So the direct proportionality is not based on the temperature in degrees Celsius, only Kelvin. Be careful with that concept. You'll see something on the practice quiz in that regard, and you want to make sure you understand that it's Kelvin, Kelvin, Kelvin. Looking at the second example, this is more of an AP example. This is very straightforward. You don't even need a calculator. It says a sample of neon occupies 3 liters at 27 degrees Celsius. At what temperature would the gas occupy at 9 liters? What happens to the volume? Increases by a factor of 3. So the temperature in Kelvin has to increase by a factor of 3. So Kelvin would be 300. At what temperature would the gas occupy at 9 liters then? 900. Just be careful. Direct relationship, direct proportionality with Kelvin, Kelvin, Kelvin only. Be careful of degrees Celsius. All right, so we've got Boyle's law showing the inverse relationship between pressure and volume. We've got Charles' law showing the direct relationship between volume and temperature. We want to look at Avogadro's principle, which shows the direct relationship between moles of a gas and the volume of a gas. So the more moles, the greater the volume. Direct relationship. So Avogadro's hypothesis says equal numbers of molecules of different gases, when you're at constant temperature and pressure, occupy equal volumes. So there's a direct proportionality between the volume of gas and the amount of gas in moles or molecules. Measurements for gases are often taken at STP, which is standard temperature and pressure, and you don't have to memorize STP. That is provided for you as well. You can see STP, standard temperature and pressure, is 0 degrees Celsius and 1 atmosphere of pressure. Any ideal gas at STP, 1 mole of any gas under these conditions occupies a volume of 22.4 liters. So 1 mole of any gas, hydrogen gas, helium gas, nitrogen gas, fluorine gas, etc., occupies this volume at STP. For example, 1 mole of neon would be 22.4 liters of space. How about half a mole is 11.2. What would a quarter of a mole be? 5.6 liters is correct. 1 mole of hydrogen gas occupies 22.4 liters. What would 2 moles of hydrogen gas occupy? 44.8. All right, no problem there. I'll review. Yes? Looks like review? Okay. In this first example, it says, what is the mass of propane gas in a 50-liter container at STP? Let's figure out how to approach this together. The problem will be yours. We want to know the mass of propane, so we're looking for the mass of propane. And we're given 50 liters of the gas at STP. How are we going to get from the given to what we want to know?
You can convert to moles and then to grams.
How are you going to convert to moles?
You put 1 mole of propane on the top and then 22.4 liters of propane on the bottom.
Then?
And then 1 mole of propane on the bottom and then the molar mass of propane on the top.
Well, this whole thing would be molar mass, but yes. 3 times 12 is 36, and 8 more, about 44 grams, close enough. Now this, without a calculator, you could get a ballpark, but it wouldn't be an ideal problem. The next one will be ideal, because it'll really simplify it easily. And you get 98.2 grams. Easy, easy. To the next one. Just be careful with fluorine gas. It's at the top of the screen. Just try and do this without a calculator. Did you get what I got?
Yeah.
Yep, fluorine's diatomic, be careful. 5 diatomic gases: hydrogen, oxygen, nitrogen, fluorine, chlorine. Bromine and iodine are not gases in their standard states. Please don't make the noble gases diatomic, they're not. Everybody got it? Yes, yes? No, no? Maybe so? Can't see? You're good? Easy, easy, right? Review, review. Easy stuff. More review. I told you it was easy today. The whole chapter on gases is easy.
Why do we have to do a chapter then?
You want to skip it?
No.
You remember everything?
No. I'm
Ah.
just asking, like,
There you go.
why are you actually giving us something easy?
What?
Why
Are you
actually
asking
giving
why
us-
she's doing something?
You want more of the last chapter?
No, 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 no.
I'm surprised.
I already told you the previous chapter's the hardest of the semester. So it's much better now. It's going to be gases, which are easy, kinetics, which are easy. We're going to get into the atom, electrons, drawing compounds, shapes of compounds, but you only did 5 shapes last year, and this year you're going to do like 20. It's all fun. And then the only other thing that's challenging in the first semester are the intermolecular forces. But we did a little bit with IMFs last year, and I think it's going to help.
But you
Yeah.
just told us, you were like, don't worry, we'll get into it in AP.
Yeah.
this last chapter going to show up again?
We'll come back to redox stuff in electrochem at the end of the year, but it's easy. Alrighty. You know that you can take all of the gas variables and come up with what's known as a combined gas law. And this way you don't have to memorize all the laws, because if you have PV over T is equal to some constant, you can see the inverse proportionality between P and V. You can see the direct proportionality known as Charles' law between V and T. You're going to see the direct proportionality between pressure and temperature at constant volume known as Amundsen's law. This is your combined gas law. So from this, we can look at the direct proportionality between pressure and temperature when volume is held constant, and this is known as Amundsen's law. And this little problem here is kind of a cutesy one. It helps to explain why you don't put aerosol containers into microwaves or any place where they will be exposed to a lot of heat. The other thing I do want to mention, since you mentioned, is yes, the chapter's easy, but working through these problems is really going to help you better understand the concepts. And you're not going to see that, you have a couple Pogel packets because they make you think, but in regard to the problem solving, many of you are really going to need to work through a lot of the textbook problems that are assigned. And those textbook problems can be found on Edline in the syllabus tab, that first day handout tab where it has course outline. That will help you. So this example says aerosol containers often carry the warning that they should not be heated. Suppose such a container were filled with a gas at 2 atmospheres and 22 degrees Celsius. And suppose that container may rupture if the pressure exceeds 8 atmospheres. At what temperature is that rupture likely to occur? So what you're looking at here is what does the 2.5 atmosphere and the 22 degrees Celsius represent? P1 and T1. And then P2 would be, I'm going to set it at 8, but I know I'm looking at it when it exceeds. And we can solve for T2. And most of you can do this. You're not going to have any issue with it as long as you are in Kelvin. But one thing I do want to indicate to you, and that is the following. You've got P1 over T1 is equal to P2 over T2. And we're going to solve for T2. Now be careful if you're ever solving for the variable in the denominator. You really want it in the numerator. Some of you will cross multiply and solve. I learned it a different way. I do what's known as a double reciprocal.
Makes sense.
So you've got T1 over P1 is equal to T2 over P2. And that's perfectly legitimate because 3 over 1 is equal to 3 over 1. If I do a double reciprocal, 1/3 is equal to 1/3. So it's perfectly legitimate and it works nicely. Now you're going to solve for this variable. You'll move P2 up here, and then from there it's just a plug and chug situation. So P2 is 8 atmospheres, T1 is going to be 295 Kelvin, and P1 is 2.5 atmospheres. Make sure your answer makes sense. The pressure is increasing by a little less than 4. The Kelvin temperature better increase by the same factor. So you have 8 times 295 divided by 2.5, and that's 944 Kelvin. So when the temperature exceeds 944 Kelvin, that rupture is likely to occur. When the temperature exceeds 944 Kelvin, that rupture is likely to occur. And you should find out, that'll be a good little project for you, let me know tomorrow, how high of a temperature your microwave can get at. They also don't recommend that you leave aerosol cans and stuff in your car, although truthfully your car doesn't get that hot.
That's weird, 'cause I have cans in my car.
You know, I don't think the heat, if you think about it, so 944 minus 273, that's not even the ballpark. That's ridiculously hot. But I do recall when it gets really cold, I used to be a very, very, very big apple juice drinker. I love apple juice. I still do to this day, but I don't drink as much, only because it's not good for my teeth. But I love apple juice, and there are probably like 7 boxes, little boxes in my fridge. But I used to, growing up, my dad owned a supermarket, so we didn't pay for food. So whenever I went back to school, I always went back with big care packages, if you will, and I always brought a case of apple juice with me. And I remember getting back up to school, and it was really, really cold and icy, so I didn't want to carry the case up because I figured I'd probably drop it. But I wish I had, because it was so cold that the glass broke. Oh, what a mess. I didn't tell my daddy that story, and now it's on film. Please don't tell my daddy. I'll get in trouble. All right. Yeah, my daddy loves me. I'm his favorite. That's on film too. Ha ha ha. Okay. That's okay. My sister's my mom's favorite. Temperature and pressure, directly related. Kelvin temperature. Be careful. I've said it numerous times. Scribble something down. You'll see the multiple choice question that I'm referring to when you do your practice quiz. All right. Now we can put all of our variables together, and we can come up with the following. What is this law known as?
The ideal.
Ideal gas law. See, you remember a lot from gases. The ideal gas law is also given to you right here. You know there are variations of the ideal gas law. Instead of putting moles in, you can put mass over molar mass. So you don't have to memorize everything. It's here. And you also can integrate density in there. Let me remind you of how. So here's the ideal gas law. Remember that the R you select is based on what? Pressure units, all right? They give you all of the R's there. One thing to keep in mind in regard to your R's, universal gas constant, they give you the one that includes atmosphere. They give you the one that includes torr. They give you this conversion. Keep in mind that 760 millimeters of mercury is equal to 760 torr. So if they give you millimeters of mercury, you can use this constant and just replace that there with millimeters of mercury. So it'll work. You'll see an example like that in just a sec. If you replace this N with mass in grams over molar mass off the periodic table in grams per mole, you get the following. So this is another one that you might be using. You'll see an example in a minute. I can derive a density inclusion formula. I can interchange these two variables, and I get PM is equal to little m RT over the volume, and then mass over volume is, of course, density. So that's another one. And one silly way to remember this, not that it's always true, some girls suffer from PMS and some boys are very dirty. And I don't know, somebody told me that I said something else last year that, okay, maybe in the evening you tend to be dirty. but nobody's going to remember that, so. I know, the other kids told me I said something else. I don't recall saying that, so I think they came up with it. I always use that same silly one. Whatever works. All right, let's see if we can work through the following examples shown here. We'll do the first one together. I'll let you try the second one on your own. You want to calculate the molar mass of a gas, so that's what we're looking for. The mass is given. The volume in mils is given. Be careful there. The pressure and the temperature. Couple things to remember when using any variation of the ideal gas law. The volume must be in liters. The temperature must be in Kelvin. So in this example, we're looking for the molar mass. The mass is 0.440 grams. The volume in liters, moving the decimal 3 to the left. The pressure in millimeters of mercury, which is the same conversion to torr. And the temperature is 86 degrees Celsius, which I'm going to put in Kelvin by adding what?
273.
Also watch your unit cancellation. It will really help. I'm going to use this formula here because I want to solve for molar mass. So I'm going to interchange these guys. And I'm going to get molar mass is equal to little mRT over PV. And it's going to be too squishy to put all there, so I'm going to do it over here. The mass is 0.440 grams. R is 62.36 liters torr over mole Kelvin. The temperature is 359 Kelvin. Pressure is 741 torr, and the volume is 0.179 liters. The only parentheses you need in your calculator are the ones in red. You don't need all the other ones. I just put them up there because it's easier to read off the screen. It doesn't matter how you plug it in your calculator. I do the denominator first and flip it. If you want to learn how to do that, I'd be happy to show you. But do whatever is going to drive the correct answer. And I get, this was in 2 sig figs, so this is going to be 74 grams per mole. And you'll see that unit cancellation if you're careful entering the quantities. You've got grams per mole. So that's 74 grams per mole. And again, in your textbook, there are several problems with the gas laws that I would highly recommend so you are comfortable with the gas concept. And some of you are wondering why I'm even reviewing it. I think it's good to see. I don't expect you to remember every single thing you learned from last year. All right? Try and do,
Dr. K,
yep,
why is it only 2?
because they gave me 86 and 2 sig figs here. Try and do the example at the top of the screen. See if you are successful with that. done, just look up and check your answer.
Why 3 sig fig?
They gave us 3. This I just did in my head, so that's not sig fig worthy. Oh, I take it back. They didn't give us 3. You're right.
Yeah, that's why I was.
So what did your calculator say before you rounded down?
1.24.
So it should be 1.2 then? Okay. Right, because you know what happened? I didn't write that initial temperature down. And they'll let you be plus or minus 1 sig fig, so they're a little more flexible than I was last year, but I do what they do this year. And again, I highly recommend several practice problems. I've listed several on the course outline, which is on Edline in the first day handout tab. Highly recommend you work through a whole bunch of problems to make sure you can do all of this like the back of your hand. One other thing I do want to show you is why this can be a little more challenging in a quiz or test format. So you've got to be comfortable with variable manipulation, solving problems, but you also need to be comfortable with any type of question that has a picture in it, a table in it, and you'll see more of this in your practice quiz. I'm going to pull this book out for a minute. Unfortunately, your book is a slightly older edition and you don't have these problems, but I've given them to you in your practice quiz. So on number 8 here, we'll work through this together. It says 2 gases are removed from their original container and placed into a third container where they react with each other. All 3 containers have identical volumes and all gases are at the same temperature. So the volume is constant, the temperature is constant. And what we want to know is what happens to the pressure. Which container has the lowest pressure? In regard to PV equals nRT, we've got constant volume and constant temperature. We know R is a constant. You illustrated it in the lab last year with lighters. You collected gas from lighters and illustrated that the universal gas constant R is a constant. So if you have PV equals nRT and V, T, and R are constant, pressure has a relationship with which variable? Moles, N. Now with PV equals nRT, P and N are in the numerators on opposite sides of the equation. Are they directly related or inversely related? Inverse. Directly related. If you have PV equals nRT, and this is constant, and this is constant, pressure and moles are directly related. Because if you got them to the same side of the equation, you'd be dividing them. So if pressure and moles, we have a couple minutes, guys. If pressure and moles are directly related, which container has the lowest pressure? A before the reaction, B before the reaction, C after the reaction. They all have the same. B is correct because it has the fewest number of moles. That's how it gets trickier than just plug and chug away. All right? The bell's going to ring in about 2 minutes, so you're okay. You've seen this question. We filmed this question. This is also on your practice quiz. Ask yourself, why containers A before the reaction and C after the reaction have the same pressure? And make sure that you can do that type of analysis. Hopefully you feel comfortable with Charles' law, Amintons law, combined gas law, ideal gas law. Next week, we will get into several concepts which we didn't discuss in honors, but they're not complex. Make sure that pre-lab is done for tomorrow. Come in for help if you need it.